All right, so if we have a question like this, the energy associated with the emitted photon when a mercury atom changes from one state to another is 6.6 electron volts. Calculates the frequency of the photon. So we need to calculate the frequency of the photon, all right? The first thing we need to do is to analyze the question, which we have done already. Okay, we've just read the question. The next thing is to analyze it and then know exactly what we are asked to find. And what we are asked to calculate here is the frequency of the emitted photon. So we write solution. When we write solution, we try to bring out the data from the question, okay? The information that the question contains is the next thing we're going to do. Okay, so let's see this energy E. Energy E is given as, where's my chalk? Is given as 6.6 electron volts, okay? But there's something here, electron volts is another concept we need to take care of, okay? So E stands for 1.6 times 10 raised to the power minus 19 coulomb, right? Okay, that's the value of E. Then the next one is what? Let's see. Of course, we are talking about energy emitted from an atom, a mercury atom, okay, from photon. So it has to do with the Planck constant. So Planck's constant is H, given as 6.6 times 10 raised to the power minus 34 joules per second. So we take care of this. And then we are asked to find the frequency, right? So frequency F is unknown. So is unknown. We are looking for frequency. Then the question is, what is the connection between the frequency of a photon and the energy, okay? So that's what we now have. Our formula is going to be, we write our formula, right? E is equal to HF, okay? That's the first one, HF. We can work with this to any length. We call it equation number one. Okay, if we're looking for F, we can still say that frequency is given as a speed of light over what? Wavelength. We call this equation number two. Okay? All right, so we can still say that from there, or since we're looking for frequency, we can use this. There's also, we can replace this. We can get the third equation here. So we can say that E is equal to H. In place of frequency, we put speed of light over wavelength. That becomes C all over wavelength. Another equation. This is equation number 3. Okay? All right, so let's see. Equation number 1 can help us because we're looking for what? Frequency, right? Frequency. So what we need to do there is to make frequency the subject from equation number 1. Okay, so let's make F, the frequency, subject of the equation. So it becomes from here, we don't have the frequency is given as energy, which is E, right? All over Planck's constant, which is H, right? So with this, we can then solve for frequency, then know the value of frequency, okay? All right, so let's go ahead and substitute immediately without wasting time. At that point, we have F is equal to for E. E is 6.6, but we must take into consideration electron volts, which is 1.6 times 10 raised to the power minus 19 coulomb, right? So we have 6.6 times 1.6 times 10 raised to the power minus 19 all over Planck's constant, okay? Planck's constant is very, very important, and Planck's constant is simply 6.6, maybe something 3 times 10 raised to the power minus 34. Okay, at the end, we are going to have that 1.6, okay? If we evaluate very well, you can see 1.6, all right? Times 10 raised to the power 15 hertz. 15 hertz. So that's the value of the frequency of the photon of light emitted from the mercury atom. So that's the value, 1.6 times 10 raised to the power 15 hertz. So that is it. This has been solved. It's been solved. But if you think the steps are not clear, feel free, comment it in the comment section. Let's discuss it further from there. All right. See you in my next class.